some paper? Yeah, I'm ready. Yeah.
It's my pleasure to welcome to Carnegie Mellon Kanna Rajan, who I've known for a long time. He's been doing some very seminal work in planning, scheduling, and execution, integration of execution, in particular in faraway places such as space and the ocean. I first knew Kanna when he was a researcher at NASA Ames. He's been involved in 2 space projects, which Kanna thinks is a record for an AI researcher. I went through all the people I knew, and I couldn't disagree with them. So he was involved in putting the planner scheduler on the DS-1 remote agent experiment, which is the first AI system in space to control a spacecraft. And worked on the MapGen planner scheduler that was used on the Mars rovers. Is used, sorry. He worked at Nambari, the Monterey Bay Research Institute?
Aquarium Research Institute.
Aquarium Research Institute, okay. As a principal researcher in the area of autonomy, and most recently is a visiting professor at Porto University at the Underwater Systems Technology Lab. Lots of long acronyms. That's from the NASA days, right? Kanna will be talking to us about his experiences in autonomous systems in space and underwater and in the air. And it's my pleasure to welcome Kanna Rajan.
Thank you. So thank you all for coming. I'm going to is this on or? It's just. It's fine. I'm going to walk you through a big picture view of what I've done, but the consequences of what and why we've done it. To a large extent, a lot of the motivations actually came from here. Dave, Reed, to a large extent, were pushing us in ways that I think now, stepping back, we've learned a lot. And a lot has to do with being in the field and learning from the experience. So yes, we publish, we write, and we go to conferences. But one of the things I learned from these 2 guys in particular was you really need to be out there to really understand what are the key issues. So I'm really glad to be here. And this is going to give you a large picture perspective. Details you can always ask me after the talk. So the talk itself is going to be a big paintbrush. I'll start with my experience in space, go into underwater, where I am right now. And on the underwater side, if you really get a grip on what this one slide does, you have an idea of what we're talking about and why I'm doing what I'm doing. It starts off with Walter Munk, who's 93, 94 now, still alive, writes for Science and Nature, the preeminent oceanographer in the world. This is the guy. And 2002, basically, he went to Congress and said, big ocean amount of sampling we're doing is just BS, because there's no way we can really understand with what the kinds of things that we've been looking for. Ocean is highly undersampled. The second part of the story has to be the founder of MBARI, who is the Undersecretary of Defense, Dave Packard. Is the same Packard as in HP. And his notion was, we really should be sending machines, forget people, to going out to sea. And the third part is something that the planning community has learned a lot about, is planning is by itself a really good activity. The plans themselves are fairly useless. So the process of planning gives you insights into what you should be doing and what you shouldn't. So if you combine these 3 things, it's really what I'm doing now. And that's sort of the motivation of the talk and where I want to go. And the big picture, the really, really big picture of why and how and what I want to do is really impacting the study of the global climate, and specifically in the context of the oceans. But the key here is really the first part, which is cost effective. And this is where I think we as roboticists and AI people are actually coming into the picture. So the outline of the talk is sort of give you a little bit of the motivating inference, the intellectual legacy where all of this sort of came through, A little bit about the decision-making architecture we're using now, because that has a lot of threads here. John, Dave, Reed, all of us have sort of put our fingers in different parts of the pie, and this is one result of it. A little bit on machine learning, or at least the motivation for why you want to be doing machine learning. Applications which really will drive home some of the reasons for why you want to be in the ocean, because there are very, very few. In fact, when I was at Embody, this was the only AI group anywhere in the world in oceanography, so which is really sad. Little bit about the infrastructure on shore, but also to say that the emphasis here is to do all of this through multiple robots. Large ocean, one robot doesn't do it. You need multiple vehicles. So there's a very sound reason for why you want to have multiple machines doing distributed control and planning and so forth. Look at the future briefly, and in the context of more academic setting as to what, these are the topic areas I've been covering, but this is the big banana, sampling. It's all about sampling, which is looking at a large space and trying to understand, gathering data and making sense of that data. And the practice, how do we do this? Well, to a large extent, my background was in AI, but I've been in these domains, space, ocean science, and I'm not a true roboticist, but I've gotten into it, fallen into it. And the idea is to do all of this together in the real world. Okay? So very quick notion of semantics, autonomy, automation. I don't think I need to say this here. I use this slide in lots of other places. The notion of autonomy is what, for us in AI, what's intrinsic is deliberation. That there is to be search, there is to be a piece of software that's deciding, making decisions, whether it's in situ or off board, but making decisions. That deliberation component is really important. So if you go to the ocean sciences, go to a person who does things in marine robotics, the word autonomy will be thrown very, very loosely, and it has a completely different meaning. But this is what I mean, and the concept of having deliberation on board is, deliberation of some sort is really important. And so the career that I've had in the last 15, 20 years has stretched from doing stuff on board a spacecraft completely autonomously, then switching on to the MER mission, 2003 Mars rover mission, which was mixed initiative planning. So there was human in the loop. And then going back at Embody doing completely autonomous work. So you throw the vehicle overboard and just cross your fingers and get things done. And then back again working with John here on an NSF project to understand what happens when you've got a bunch of robots, when you throw in this really non-deterministic agent called the human being into the mix, what happens? And the consequence of having a human in the loop in controlling robots. So that was a NSF project we just wrapped up recently. So that's sort of been the overall theme, and in all of this, the idea is now to go to the next step, is combine all of these elements, look at the ocean, at a chunk of the ocean at one time, looking at the same part of the ocean through different modalities. Aerial, surface, underwater, but more recently also space, and I'll get to that right at the end. Okay. So why inference in the ocean? Why? The ocean is large. We understand very little. You can turn on the radio in the morning. You have a pretty good idea of what the weather is going to be like here in Pittsburgh, because atmospheric research has been going on for years, decades. Huge amount of money for the Air Force, Army has sunk in, and so we have a good idea of the weather forecast. We have nonlinear, highly nonlinear models running National Weather Service, which give you a reasonable idea of what's going to happen. Zero on the ocean. There are models running, and there is a concept of a model, but the accuracy of the models, what's called the skill level, is very, very poor. Especially in the coastal ocean, which is where there's what we call as mixing. The waters get really churned up. It's close to a zero understanding what's happening. Opportunism, because we don't know much, we want to be able to go out and discover what's happening, what's interesting. And this is across the board, biology, chemistry, geology, and everything in between. So we're talking about the ocean as being an area which is so poorly understood that really stepping out with a boat, making measurements is a big deal. So using the notion that we know so little, you can deploy robots, bring data back, and do something that is opportunistic, where you've seen something interesting and do the analysis and come up with theories of what's happening. That's where things are right now in the ocean sciences. There's a whole host of other reasons, but getting a lot of data, sensors are now relatively cheap. Robots are getting cheaper, not very cheap, but still getting cheaper. And to do things in a very sustained way. Typical oceanography as experiments is you take a ship, huge crew, $10,000, $15,000 a day, if you're lucky. It's usually about 20, 25. Go out, take measurements, and measurements are done by what's called drilling. You throw instruments in the sea, the ship has to stop, take measurements, bring the instrument back, and then keep going. So stop and go, stop and go. And then out of these point measurements, you come up with this grand theory of how things are changing. Right? So the notion of continuity, processes are continuous, but the measurements are not. So it makes no sense of what's being done at this stage, by and large. Robotics is changing it, but very slowly. So there's a huge amount of opportunity and reason why we want to do inference. But there's also the standard conundrum we all know in robotics, which is finite time, energy, resources, and so forth. So these are all conflicting resources, conflicting ideas that you want to be able to balance. And one way in which you want to balance is, what's the here and now? I don't understand my environment. It's not mapped. It's not clean lines in a laboratory. I can't do SLAM. There's no structure. So if I'm throwing in a robot, what do I do? What do I know now about the environment that I can capitalize on as against what I have to be doing in the future? So it's this balance between a goal and the near-term opportunism. You see something interesting, a variation in the CTD profile, which is conductivity, temperature, density. You see something interesting, what do you do? So that balance is where I think decision-making comes in and dealing with the fact that you have to work around time and resources. So lots of motivations doing adaptive science in the ocean, doing it at a large scale. For me, using formal methods, but which are very applicable and scaling, which can scale into multiple vehicles, multiple robots. And to doing it in a very sustained way. And the idea is to impact not just the field itself, but to a large extent impact how you can make changes to how science is being done. Oceanography, as a former boss of mine said, who is now the editor of Science, she basically said, we're doing the same, and she used the word, we're doing the same shit we're doing that Charles Darwin did 100 years ago, which is true. We really are. So that motivation is to bring in new methods, new approaches to how we want to do oceanography. So a lot of what I'm doing now is there's a continuum, and so I'm just going to briefly go through the continuum. It starts off with the work at NASA, which Reed mentioned, which was in the remote agent, which was the first closed-loop AI-based system in space. So essentially, truly autonomous operation. Reed was part of that experiment. 1999, we flew a piece of software which you see in green at the top left, which did onboard decision making, which did planning, execution, and failure recovery, all on board for the first time. And I believe that's the only time that's been done, as far as I know. There are some papers associated with it. This is probably the most prominent. That was 1999. And one side effect of this was the impact on academia, which we had never counted on. And this was a slide from Nils Nilsson's AAAI keynote lecture at that time, which was Turing on one side and remote agent on the other. So that took us by surprise because we were just doing our own thing. And here comes Nils Nilsson saying, "Wow, this is such a great deal." And then, of course, we had cheap thrills having pictures taken with McCarthy and of course Mr. Star Trek right here. So fast forward to 2003, 2001, we got onto the Mars rover mission at that time. This is the earlier rover mission and the first real science rover mission. The system in question is called MapGen, and it's a planner. It pulls together scientific and engineering constraints that are needed to run the rover's operation fully autonomously next day. But the concept of autonomy here is mixed, because the decision making happens very early. You construct the plan, and then essentially the entire plan gets uploaded, and essentially you execute through the sequence of activities. So there's no in situ decision making, in other words. Mixed initiative on the ground. 2004, this was a research, essentially all research code, and we thought, as everyone thought, was that this is going to last for 3 months, the entire mission. There are 2 rovers, one of them is dead, the other one's still operating. And this system, which was purely for 3 months research code, which we had sort of crossed our fingers on, is still running. So I believe this is the longest running AI system anywhere, and still in use. So that's sort of where the planning part comes in, planning and execution. I'm going to sort of skip through a bunch of these things, but I wanted to show you this particular, a little bit about the excitement of doing things in the field, especially when the field is about 65 million miles away. This was one of the early days, the very first plan that we executed on board Deep Space One. Spacecraft was 65 million miles away. We were running a language on board which most of you don't, which we, of course, old-timers do, which we love, called Lisp. This is the only time Lisp has flown in space. And
I'm sure it will be.
It will be the only time. If we were to repeat it, we'd still do Lisp. I would do Lisp. Come on. You're still doing Lisp. So this is a real story, and this is to tell you that we have a conception of what AI does, but actually that conception of AI is actually very weak. And this is just an example to show you that decision making has a very myopic view, the way we look at it, because we always think that the machine is going to do certain things. What you're seeing here is this is actual data from the experiment during flight. Spacecraft was 65 million miles away. There's a test bed, an identical piece of hardware at JPL, pretty much in the next room. And we were all sitting there tracking the data from the 2 different streams. What you're seeing here is a standard chronological search tree, the exploration of it. Wherever you see these bumps, you're seeing backtracking. Okay? So you're looking to build a plan, and in the process of building a plan, you're using chronological search. When things don't agree, you backtrack. So this is where those points are. So there are 2 streams here, one from the spacecraft, one from the actual hardware, the identical hardware on the ground. Now, if things had really been so focused and tested well and actually worked the way it should have, or the way it's advertised, both these streams should be identical, because essentially we're running the same piece of software on the hardware in space and on the ground. Right here was the very first heart attack that Nicola and I had. We lost 10 years of our lives, and we thought AI was doomed because our planner was doing something completely different. And the reason is here the divergence between what the spacecraft was doing and what the hardware testbed was doing. And you can see this, we're talking about at least 45 minutes here. So we were losing parts of our lives. You see that thing, death, when they say you see all these pictures and images of life going by, that's what it was. So in the end, bottom line wasn't bad. In fact, it was very good, because the planner on the spacecraft did find the right plan, and it did execute. Everything was fine. It just happened to be a different plan. And the reason for this difference was because the configuration of the spacecraft was different from the hardware. One file, and this was just a star catalog to figure out which stars to navigate. There was a slight difference. So the moral of the story here is that had this not been an AI system, it would have crashed and burned, I think. I think the fact that we were making decisions, making it autonomously, using very systematic rules on board, actually really helped. Fast forward to the MER mission, and again, all of this is in the past. What you're seeing is, this is to motivate about what we are doing on MER even now to this day. The timeline of decision making, this is very, very human centric. The decisions are made on the ground with humans, scientists from the US, Denmark, Germany, I believe, and Switzerland. And the whole process is very, very structured. So it's not as if you walk in and say, I want to do X on Mars tomorrow. It doesn't happen that way. There's this whole sense of deliberation, finding the status and merging what you know of the robot with what you think you want to do. And then there's a lot of back and forth in terms of horse trading between different scientists wanting to do different things. So that's what the lay of the land is. Rover goes to sleep around 2 in the afternoon, Mars time, which is 2 hours, 24 hours, 40 minutes, and a few odd seconds, one sol. On day 40 minutes, something like that. So it's off by 41 minutes, the Mars time versus Earth time. So rover goes to sleep around 2 o'clock in the afternoon, wakes up at around 8, and that's when all the activity on Earth happens. And this could be at any time because Mars and Earth time are not coinciding. So we'd go in for our shifts at 2 in the afternoon 1 week. 2 weeks later on, we'd be doing exactly the same thing inside the pit at 2 in the morning. So it's all of the activity is happening here. The interesting part is lots of meetings that you're seeing. The green is science, blue is engineering. All of these converge on this spot, which is all the engineers have said, here's what's the status of the rover, here's the pose, here's where we think it's gone, here's the amount of energy, and so on and so forth. This is a solar-powered rover, keep in mind. And then the idea is to merge all of this to decide what's the next thing we're going to do tomorrow. And this is where our system is in place. It's mixed initiative. There's a screen, there's a human operator, and they are going back and forth. The machine doing planning, and the human being making changes and trying to figure out if he or she can compress, add more activities to the rover, right? So that's sort of the crux of what MapGen is doing on MER to this day. There's a video here, but I don't know whether I want to have the time. But very quickly, here's what the negotiation process goes. It's horse trading, basically, right? So these are all the key players on doing Mars science sitting around a table trying to figure out what's the best thing to do, given this is once in a lifetime opportunity for many of them, right? So there's a lot about what MapGen does. I'm not going to go into it. There's some notion of impact between these two very different systems, onboard, remote agent, on Earth with mixed initiative with MapGen, and that's some of the impact. One interesting impact is on MapGen. For the first time, I believe, we were actually able to show the return on investment to NASA. $4.5 million invested over 3 years. The return on investment was calculated by the cost of the mission amortized over the number of days for which it was supposed to be. We got the return on investment in 1 week for the 4.5 million. And this they bought. So I don't think we were able to show that return for DS1. Lots of lessons learned. I'm not going to go into it, but I'm going to sort of switch modes and start talking about planning and execution, what I'm doing now. So let me just stop briefly and ask if there's any questions, queries, comments. Nope. Okay. So as Reed mentioned, my interests are in getting machines to do something interesting. We all have in different ways. One part of it is the notion of planning, looking in the future and projecting in space and time, and then using those plans to execute while being in an environment which is potentially changing and depends on the rate of change. If you are on Mars, it doesn't change that much. If you're in a museum here with human beings going, yeah, it changes a lot. The general concepts are fundamentally the same. You have an abstract planner, which is deciding what needs to be done. There's a controller, which is synthesizing commands to the low-level hardware. And there's the physical system itself, the hardware, which is executing those commands. And then the world is telling, through the hardware, what the world is expecting, or how it's changed, or what are the implications, what are new things that are coming, events in the world. So we call them observations, they're actions. This is very standard terminology, right? I may have even stolen this from one of your papers, I don't know. So very standard. This is the way we look at the world in a very discrete system. And this sort of boils down to looking at the sense plan act mechanism as a three-layered architecture. So three-layered architecture is very, very, very common, very standard. And the idea of showing you this is to connect it with what we are hoping to do. But before that, the notion here is why is planning and execution important, and why is in particular interleaving planning and execution important? If you look at this old video from 71, Shaky, which basically says, here's a robot, there's an obstruction. Now the robot's sitting in front of the obstruction saying, okay, what do I do next? It may be okay in a terrestrial environment. Underwater environment, our vehicle do not stop, cannot stop. We can't afford to have this notion of what do I do next. It has to continue. And so planning and execution are interleaved and intertwined. You can't plan and then execute like we did in the remote agent. You have to have all of them working together in a seamless way. So in this case, the assumption was the world is very quiescent. Nothing's happening. But the world is never quiescent. Even in a very standard lab environment, things are changing. And certainly in the underwater environment where nature is hugging your robot, it's not, it's changing all the time. So we've been looking, a large number of us, looking at these architectures, what kinds of ways in which, how do you assemble these blocks? We know planning, we know execution, or we think we know, and how do you pull these together? So the original three-layered architecture sort of morphed, looking at the notion of how you deal with time. Time in robotics is fundamental. You can't just execute discrete actions without really understanding the implication of when you do it, and more importantly, in what context you do it. So when you think about how you need to deal with time, there's a whole range of options. The one option that we took is time is intrinsic, and we reason about time in our representations. And that work is basically called temporal planning, and there's a range of ways in which you can do temporal planning. But early work came out from LAS in Toulouse, and simultaneously we were working on a system called IDEA, which I believe ran on one of Dave's machines. And then we've essentially taken what was the core concepts of IDEA and built a system called T-Rex, which I'll talk about very briefly. Philip actually worked on T-Rex here, right? So now I'm switching into the AUV world. We've left the space thing at the back. AUVs, underwater, autonomous underwater vehicles. And all this is telling you is early AUVs were doing very sequential, script-based commanding. Where we'd like to be and have been for the last 5 to 6 years is doing planning on board. This is pretty much the only operational system anywhere in the world doing planning. There have been previous attempts, but they were sort of one-off experiments, right? But where we'd really want to go is having a multitude of vehicles, different kinds of vehicles, in the ocean, over the ocean, and on the ocean, right? And the way to understand this concept of what we are doing is to start with something very simple like any complex system. And I'm showing a remotely operated vehicle, which is a tethered robot. But you can think of even a car as a complex system. And when you look at these vehicles that we have, they have levels of abstractions which are different in 2 ways in particular. First is any vehicle has a bunch of actors associated with it. In the remote ROV, remotely operated vehicles, there's the vehicle itself, the physical entity. There's a pilot, there's an arm operator, and there's a scientist. They all have different things to do, different activities, and at different levels of abstraction. The vehicle has to be extremely quick and fast because it's responding to commands, hardware commands and actuations. The pilot and the arm operator are somewhere in between. The scientist is stepping back and looking at the entire mission for the next 15, 20, 30 hours. Right? So there's a temporal component for decision making, and then there's the functionality of what people are doing, actors, different actors. And the same thing in your car, right? You're sitting down as a human being, you're sitting down, your heating system, your air conditioning system, your engine, your battery, they're all different subsystems working at different levels of abstraction. So what we're looking at here are two scopes, the temporal and functional scopes, which are different and orthogonal. And they're doing functionally very different things. And each of those boxes that you see, they're essentially controllers. You can close the loop within those controllers to do fully autonomous operations independently of the other in most instances. So science payload operation can be completely independent. Of course, it needs input and output as to what it needs to do, but what's inside is a black box. And that is sort of the basis for this system architecture called T-Rex, which is Teleo-Reactive Executive. Not a very great name, but that's what we went with. And the notion here is exactly what you saw earlier. Each of these is a planning execution system, each of these boxes. And we call them reactors. Each is standalone. One can be written by Reed, another by Steve, and so on and so forth. And we have a framework on how to pull this all together. The notion of how they interact is through goals. Goals are the green arrows from top to bottom. And essentially, each reactor tasks the other reactor with a partial plan or a set of goals, saying, I want you to do this. Each of these has a very specific notion of what its expertise is, which is why different groups can build these. And the magic is in the interface, how you actually translate and communicate. Goals go down, observations from the world go up. And the notion that they are separate has two advantages. One is partitioning the knowledge. The other is the notion of failure. From the remote agent, we learned that the closer you are to the lower you are down in dealing with the hardware, the better it is. Because the more abstract the hardware software failure becomes, as it comes up, the more expensive it is computationally. If you can avoid replanning because of a failure, that's a good thing. Which is why on DS1, we had something called MIR, which was a diagnosis engine, which was at a lower level of abstraction than the planner, which was working at a higher level of abstraction. So if there was a plan that failed, that would cost us quite a bit. But if dynamically you could reconfigure the vehicle in doing diagnosis and fault recovery, that was much, much more optimal. And that's really the story that we have here in abstraction. So observations go up. The world is saying, here's how the world has changed. Goals are coming down. And there are multiple boxes. And this is an instance of the number of reactors and the way in which we've designed it. That's how we started. We started with 4. Now, the kinds of operations we are doing at sea, we have about 8 of these boxes. So it depends on the application. Right. And the thing here is, again, abstraction means this is closer to the hardware. There's more reactivity here. There's more deliberation up at the top. Right. And the consequence of this is also this system has to be very, very well engineered. When you're dealing with validation, there'll be always some person coming back and saying, how do you know it works properly? Well, we don't. But if we can get to verify this part and make this bulletproof and make sure that a failure recovery is safe in this context, right at the bottom, the rest of it can handle itself. So there are all of these threads of software engineering, how do we build systems, failure recovery, of course doing planning and execution, how to partition it amongst different groups and people. That's all factored in here with the notion of building systems that are sustainable over time. And in each of these, the closer you are to the hardware, the lower the latency, which is how quickly you can generate a plan, and the look ahead, how far you should be planning. The further you are, the further planning that you do, which can, of course, keep changing. the lower you are, the less that you do. And what you're seeing is an early version of the PR2, which actually used T-Rex on board for doing the first internal demonstration. It's on the web, and you can look it up. And this was a ESA project that we worked on with some of our European friends to demonstrate a long-term autonomy project on the surface of Mars. And this was all at LAS in Toulouse. So that's sort of the gist of what the system does. There are lots of applications that, if I have time, I'll sort of get into. But there's a whole host of papers about the system itself. Primarily ICRA, IROS, AMAS, and so forth. So here's a quick idea of an example of how this thing works. There are 3 reactors. This is just an example. Okay? And the way they're communicating with each other is through a notion of timelines. Timelines are essentially system variables that you're tracking in time. And this comes from control theory. And the notion that these you can track a system variable over time boils down to building small, simple, finite state machines. So each of those timelines is a finite state machine. The catch is, when you start building more and more of these timelines have to interact and communicate with each other in ways that makes the machine do things which are interesting. That's the black art. And that's something that we still haven't figured out. We are doing all of that by hand for now, but we know how to do it. So you have these multiple timelines. What you're doing is you're communicating between the timelines by simply copying. There is a notion of an external and internal timeline. Internal is something that is owned by a reactor. So you see this thing is called path. This is owned by the navigator reactor, and that same path is up above. Essentially, this is a copy-paste mechanism as a means for communicating. So what happens is, in the most abstract reactor, you are hypothesizing a plan that you would like to do. And you dispatch that as a goal to a lower reactor to say, here's what I think you should be doing. So then the lower level reactor takes that as a goal and has the competence. Assuming it has the competence to deconstruct that goal, it does. And it does that here. So the goals are coming top down. And the deconstruction of those goals happens here. And it happens in a very particular way. There's a little bit of math associated with it. Because we don't want to plan too far ahead, and the planning too far ahead depends on how far you are on the stack, there's a little bit of computation in terms of how you do that, which is in one of the papers. I'm not going to go into it here. And so once you deconstruct the plan, in turn, this reactor has timelines coming from down below, which it suggests to the lower level reactor. I think you should be doing X or Y. And that's where it comes down. And then bottom up is, once you've executed, the world is telling the system, OK, you said open the shutter of this camera. Here's what happened. And you get the status going back. If the status matches the expectation going all the way, or wherever that particular activity was deconstructed, you're set. And if it isn't, then there's a problem. And then you have to reconfigure. Okay? So that's sort of I'm going to skip the slide in the interest of time. But that's sort of the intuition behind what's happening. And I'm going to dive into applications. And there's a whole range of things here. And I'm also seeing people drifting off into sleep. So I'm being reactive. So any questions at all about the system itself? Any comments?
So one of the things I remember from the remote agent days is that all the boxes had models, and all the models were a little bit different.
Yes.
And that was a huge problem. In the 15 years since then, how has that been addressed?
So the one thing that has been addressed, the models will still be different. You can't change it. But one thing that has been addressed, which I believe is one of the key parts of what this is sealing that capability inside one reactor. The problem with what we had was I was talking to your system and you had built your system with a set of primitives. My primitives then had to match yours. And at some level, we do have that issue here, but in a sense, as long as we agree on what the interfaces are, by and large, that goes away. And your system, so the example here is we worked with Maria Fox. Maria built a learning mechanism through a decision tree on how to follow a bloom, a patch of water, a bloom in the water column. Supposedly in 3D, but she actually did it in 2D. So essentially there was this entire decision tree which said, I'm sensing and am I in or out? And if I'm out and if in my past I had been inside the patch, then I'm out, which means I need to turn right, those kind of decisions. She built that entire tree, encapsulated within one of these boxes. We helped her with that. And essentially we really did plug and play. In 1 week's time, entire integration. She did hers in the UK. We integrated within 1 week, we were out at sea. And she had a gross idea of what to do, but we told her exactly what kinds of interfaces we want, timeline based. So I think we have a story. I'm not saying this is the greatest, but I believe this is one way of isolating that problem. And one of the things here is that we want people to be able to have different competencies and different groups working on complex systems, they're contributing together.
So where would that model fit there? I mean,
each of these has its own model.
Right, so did Maria build all three of them?
No, she just built one. And essentially this whole decision tree was her model. Okay. And it was fundamentally different from what we were doing. You've seen our models, right? It's the DDL style.
Yep.
You described the control structure serially, and I don't think it probably is serial, in that you're looking from top-level goal to low-level goal and then back up. Is there lots more bouncing about, parallelization?
Well, it's in one Neumann architecture, so there's no parallelism per se, but yeah. The concept is there, yes. The one thing here is a branching factor. Right. Suppose you have one reactor and two of these children here. Suppose they come to different decisions. Then what does this do? That's open. Now that's where the magic happens, where we design and test the hell out of our system to make sure it doesn't. So there are lots of open issues about how to deal with it. The interesting part is here is the fact that we've used this, we've taken the lessons learned from Remote Agent and other projects to say, how do we want our friends to work with us? How do we partition, and how do we make sure that when we have these kinds of role-playing, different groups working together, how can we assimilate? And that's what the framework is. It's the framework, not the fact that we are using temporal planning or any particular kind of planning. That's irrelevant. So in fact, one of the goals is to actually start looking at local search for certain problems in one of those boxes. And actually hunting for things in the ocean, local search is really the right way to go. We haven't done it yet, but that's the idea. So completely different algorithm. You can have a neural network, for instance, inside for all I care, but we haven't gone that far out. So by way of context, this is not vaporware. We've been in the water column at depth of more than 200 meters with our vehicles continuously for the last 6 years. And when I mean continuously, I mean fairly continuously. Operationally, some of the missions, one of the missions I'll show you very briefly, has been continuous for a week and a half in the water, 150 or 160 miles off of the coast. Right. Now, one issue is what's the complexity of those missions? The complexity of those missions, to a large extent, is around the kinds of applications you want. And I'll show you one which is a little tricky. It sounds simple, but it's a little tricky. But before I get to it, here's the embodiment of the vehicle that we had, very large AUV, about as big as this table, required a big ship. What you're seeing is the stack, which is on board. You're seeing a video of how we used to launch and recover. right? So you need specialized equipment, not like John going into the river and, right? That's the idea. Thank you. And then the water samplers. The water samplers are actually a game changer if you are an oceanographer, because that changes how you go out to sea and why you go out to sea. You need the water samples. Instead of getting a whole ship going, you send a robot. Right. So that was the Embari vehicle, very briefly, fairly expensive, $1.5 million, just the vehicle. And
If you go back one, I just want to, so it says needs AUV adaptability.
yeah, so,
sampler.
okay, so I skimmed on that.
Why couldn't you just like put one of these off a rope and tow it behind you on the ship?
No, actually, I was thinking you'll ask a different question, which is why do you need the adaptability? And let me answer that first.
Okay.
So,
Because I know the answer to that.
yeah. So, 10 bottles.
I was going to start with a simple question.
Hang on. It's a simpler. Actually, it's a more complex answer. The 10 of these bottles, right? So you send the vehicle out. Each sampler you get one shot, right? Because you don't want it to be contaminated by other samples. One vehicle, one mission, 10 samplers. So it's a resource limitation problem. The way they had conceived of this is by standard waypoint navigation, getting the vehicle to do its lawnmower, and then magically there's a guy sitting there and saying, oh, I'm in this patch of the water. I'm pretty sure, let's trigger a sample here, let's do it here, off the top of his or her head, mostly his head. And our notion was, you have a goddamn robot, it can sense, why the heck aren't you closing the loop? And that's what we did. So this was actually a big deal, which is closing the loop on board for sensing, for returning a water sample. And they never thought of it that way. And it's for roboticists, that's the most obvious thing.
So what are they sensing in order to make that decision?
Well, so the multiple parameters, the CTD, conductivity, temperature, density is the standard. Fluorometry is really crucial because that gives you a notion of the chlorophyll content. We tried and did not get into laser-based or optical instruments to integrate that in. But what we did was we used, I'm trying to remember, can you, what was there's one other instrument on sediments. Do you remember? Turbidity? Turbidity, but it runs off of turbidity. So there was one other sampler, one other instrument that we actually used. So there are different combinations of it. One application had to do with looking at, I'm going ahead of myself. But did I answer the sampler question or no?
Yeah, I misinterpreted what it was. I thought it was a continuously sampling
No,
measure.
it's discrete. You
Measure.
take one shot and that's it, you're done.
No, I don't understand.
Okay, so that was the sampling / machine learning problem is where do you sample? Large ocean, 10 samplers, one mission, right? So there's the standard notion of machine learning, how you have a prior because you've run multiple missions in that patch of the ocean, roughly approximately at the same time. And John and I were looking at it from a slightly different perspective through remote sensing, if you remember, to build up the priors. But this is the same notion. And then when do you sample? So this was partly initially with Maria Fox, which is doing very simple k-means clustering and getting a cluster-based approach. But then we started getting into more the temporal aspect using Markov fields, Markov random fields, and Markov processes to actually to build the sampling mechanism. When do you sample and trigger? And here is an example of the fact that this is old data through previous missions that you're seeing at the top, a simulation, MATLAB simulation. What you're seeing is a transect which is V-shaped over the Monterey Canyon. It's about 11-kilometer transect. And the thing is, the red part that you see is sediment rising from the bottom, coming up. It's episodic. You can't predict when it is going to happen. And the thing is to know what's in the sediment because the nutrient mass in the water column is always at the bottom. Variability in the ocean is along the vertical, right? So for this distance, if I sample here and if I sample there, it's useless. It's the same thing. But for that distance, if I go vertically down, it's fundamentally different water. So variability, and you can see that very easily here. Look at the water temperatures at the top, and I believe this is temperature. No, it's backscatter, but it's a measure of the content of the turbidity of the water column. It's fairly uniform at the top. So wherever you sample in that 11-kilometer V-shape, it really doesn't matter in the top column. But when you go along the vertical, you can see that there's a huge amount of variability. So think of any parameter, nitrate, temperature, density, salinity, they fundamentally change in the vertical. Sure, if you go a little bit further, say 2 kilometers away, yes, along the horizontal things will change, but in terms of the variability, you really look at what's in the vertical. That's the reason why AUVs, when they're in the water, they're going up and down. You're yo-yoing in the water column, because you want to get a good measure of the spread of the readings that you get by not going flat and straight. Right? So here the problem was, this is episodic. We don't know when we see it. Sitting with a ship on top doesn't make sense. Can a robot do the job? And that's really what we're seeing here. Essentially, it's called intermediate nepheloid layers, these layers coming from the bottom. And sampling, and what you're seeing is the probability of sampling in the red fields there based on the past. So we've constructed this field. So this is post hoc. And what you're seeing here is where the samples were taken, right there, right? So, so there was a hidden Markov model that we were using, which had the temporal component. And so based on that, we were able to, using a lawnmower survey, we were trying to figure out how far the separation should be. If I'm not sensing the field I'm in, there's no point in having my next survey line very close by. Having it as pushed as far apart makes more sense. Right, so all of this is decision making on board, looking at fronts or thermal gradients, two bodies of water along the vertical or horizontal which touch each other. That's where the biota sort of get entrapped. How do we track that? It's a nonlinear moving system altogether, and how can we track that in space and time? So what you're seeing is an actual mission where there was mixed initiative for the first time. There was a scientist sitting on his desk. He was getting data every time the vehicle would pop up to the surface. He'd get a partial run, a dump of the science data. The field was being reconstructed in MATLAB on his desk, and he was seeing in real time the field being constructed. Again, it was 11 to 12 kilometer run in the water. And then he is making he's making a decision to figure out where he wants the water sample to be taken for the vehicle that we saw in the previous slide. So in this case, what he did was to draw a straight line and said, that's the point where I want the vehicle to take a sample, because that's the gradient range that I want to sample. And so this is mixed initiative. A system is making decisions on board. There's a human being on the ground, and we are communicating via satellite link. So same issue with ocean fronts, but with two vehicles. One being a little bit more capable with the right sensor. The other is the Dorado that you saw earlier, which had the water samplers. And here what you're seeing is a front, a gradient, cold water, hot, warm water from the shore. And this is where the interesting part is in the boundary. So finding this and actually doing something with it, that portion is where the decision making comes through. You had a question?
Yeah, so just a clarification question. You have this really dense gradient map, and that was gathered with 10 samples at a time?
Continuous. We are operating with a vehicle which is operating, the sample rate is about, 100 hertz, I believe.
I see. So this is different from what you showed before with the 10 samplers.
That's a different application. There we are sampling, so there are two words here, sampling and actually taking water samples. They're two different things. Mm-hmm. You're sampling the ocean by taking measurements continuously. Mm-hmm. Just like you don't turn on and off your laser rangefinder on your terrestrial robot. It's sampling continuously. Same thing here. Okay. This was where we started diverging into looking at Gaussian processes, because the question was, when you have multiple vehicles, how close do you want them to be? If these multiple vehicles are sampling the same stretch of the ocean with roughly the same instruments, the more variability there is, the better there is, because then you are building a map which actually shows you how far a particular phenomena is. If they are too close, it's fairly irrelevant. And the experiment was having a device called the wave, what is it called? Wire walker. The wire walker was a green device powered by wave energy, and it essentially has a CTD going up and down. The CTD is like a thermometer for the ocean. Standard device. Conductivity, temperature, density. This is floating completely on its own, and the vehicle has to go around, find it, and go around it, essentially. So essentially, this is moving in a non-deterministic way, and you're doing tracking in the ocean. Hands off.
What's the point of going around it?
Well, because you want to see how big your spatial sampling should be, how close can you be. And you can, if you're sampling around it, essentially you're following it around. So it doesn't have to be a square or a box, but it has to be in near vicinity. So the question was, how far? So this is where we started getting into the spatial statistics part, where trying to understand how we do multi-vehicle control for sampling, but it's all based on this notion that we want to understand a stretch of the ocean. So in all of these, we were experimenting, working with biologists, but what was missing was on the shore side, we had a ton of data, and we didn't really know how to pull this all together to do visualizing and planning and control, letting scientists run the show. So this was a project that started at Embari called ODSS, the Decision Support System, sort of like a mixed initiative kind of a thing, but a whole bunch of other things, doing analysis, doing machine learning, and stuff that we were hoping to do with John and his students here, which is use that as a repository of data to predict how things would be happening, and then figure out what kinds of experiments we could do. So the blurb here is about looking at a feature of interest, range of different features, but having a back end which would deal with collaborative approaches to doing planning, doing modeling. Visualization was quite a big deal, and planning and doing learning. Huge trove of data sitting somewhere in a repository at Embari. How can we use that to predict what we are doing now in the next half an hour? And the notion here was we want to go to make it into a very usable mechanism, having it on the web certainly, but also you could be sitting in Botswana while your vehicles are in Monterey, right? You could be planning and having a chat session. You can be deciding, marking plots that have come out and demonstrating how you could use the data that you've just acquired to hypothesize. So all of this is a mix of the Mars work, mix of the stuff that we saw while going to the sea, and it's all sort of getting gelled together. So this system has been built, it's operational, and not all aspects of it are in use, but the scale of the kinds of things, what you're seeing is the Monterey Bay, which is the largest chunk of the ocean studied anywhere, the most studied chunk of the ocean anywhere. And this is about, it ends about here, it's about 30 kilometers. And this is what's called a mesoscale. It's about 50 square kilometers, which is really the basis for doing science in the ocean. A mesoscale is the single unit that you want to start with. It's large enough, but it's not too large. And so what you're seeing is the track lines from 29th September to a month later in 2010. And these are the kinds of experiments, the tracks of lines. It's not scientific data, but it's just track lines to give you a notion of how dense the sampling was. And this is still undersampled. So what
Those are vehicles moving around?
Vehicles, ships, airplanes, the Navy was involved.
Yeah.
Right? So there's a whole bunch of different, and we had about 15 or 20 collaborators for that experiment, and those are continuing now. So this is just to give you a scale of the ideas. So moving forward to where I moved to Porto, our early work with Porto was in looking at how we can combine different elements, robotic elements. And we started by looking at making simple experiments using a Portuguese Navy ship to fly UAVs and to have AUVs in the water column. And the general idea was, looking above from the sky, can we spot a feature where we can send an AUV, right? Very reactive mode. And then the two of them magically coordinate in some fashion over time and space. So starting with July, in October they came over to Mbari, and so essentially we've been working together out in the field, and then and then going back to do stuff in the ocean in March. What you're seeing is a vignette of things out in the ocean with the capabilities. None of these are expensive. AUVs, and I'll show you in just a minute, are reasonably cheap. We are talking about UAVs, which are about 1,500 euros, 2,000 bucks with sensors. So if it falls in the drink, it's okay. It's not too big a deal. And then landing on the ship. So I don't know whether you saw that, but I'll show you in just a minute. So this is 2013. So you see a takeoff, and that's sort of the landing that you can see with the net. Very, very simple stuff. And you can get a lot done scientifically. And so you see the class of AUVs where a bunch of 1 or 2 people can really pick them up and go. So this is very different from the Mbari style, big machines, ships, and so forth. And it's become even better. This is what I was suggesting as one of the things to think about in terms of an AUV, dispatchable. So early experiments started in 2013 on, if we start doing aerial, surface, and underwater, well, what are the things we need to look at? One thing was very clear is we need to have coordination at some very, very loose. Coordination and rendezvous. The rendezvous part was because our phone bills were very high. Right? If you start using Iridium all the time, your bills tend to be pretty high. So the notion here was we'd have what's called a wave glider surface platform, green energy, which is a 2-bodied system, which we could always borrow. And because it's a surface, has a surface expression, and because we were in coastal areas, we could do 3G or 4G, dirt cheap. But the vehicle was talking Wi-Fi. So from Wi-Fi, we talk to dump our data on the wave glider, which would magically rendezvous, and then we would take it from there. And this has gone further. That was 2013. Now we can do acoustics, Global Star, Iridium, something called DTN. I don't know how many of you know what delay tolerant networking. Are you aware? So, okay, it's basically doing space comms where there are delays in between. So it's not your stream of data or packets. And we can do Wi-Fi and all of this together in one box. So all you need to do is plug the box to power source, stick it on the boat, stick your acoustic comms below, you're set. And so all of this is stuff that was built over time at FEUP in Porto. And this is sort of a quick blurb of what the lab has. And it's a subset, the number of vehicles, the hardware, and so forth. All of these fly, they're all operational, right? And lots of places where the lab goes, it's very, very field driven. So pretty much you can never find the full lab in the lab ever. There's always, even in the worst, whenever it's blowing in the winters, there's always patches of the Mediterranean. There's always somebody who's saying, well, do you mind coming over? And so there's a lot of experimentation that goes on. This is the vehicle, and if you look at this video, that's how we launch now. We just take the thing and just throw it over.
So there are clearly economic advantages of having a much smaller vehicle. Are there technical advantages?
Which way?
Over the Mbari class vehicles. Are there technical advantages of having something this much smaller?
Well, the one technical advantage is that the Mbari vehicles have been frozen in time, so the sensors they have are older. And they are getting, these form factors are becoming much more manageable. Not all, but many of them. And so it's getting cheaper to actually fly and build and integrate, not to mention their energy consumption. So this one, this is the latest, greatest model. It can go for 24 hours. This is the one I was telling you about. 24 hours, comes with IMU modems. I don't know about side scan, but it comes with certainly a forward-looking sonar and a CDD all together, and a DVL which tells you speed over ground. It's for 125,000 euros, about 150, 160, which is dirt cheap. This is cheaper than the cheapest AUV you can get in the US, and these are robust. This is how we launch, and recovery is relatively similar. Obviously, it's a little bit harder, but fundamentally, the scale at which we are doing, because it's low cost, it's portable, it makes things, the whole logistical aspect of it, it reduces the burden. Right. And this is a Chinese-made UAV, very, very effective, X8s. Lots of people use them. And we've been working with our friends in Norway to put, we started putting infrared to look at thermal gradients. We are going to start put in July hyperspectral imagers built by their defense agency, and start looking at what we can see. In July, we'll be in the Azores, middle of the Atlantic on a ship, and we're going to be chasing whales. And most of the time, we're going to be looking at what's the whale excreta. That's really what we're going to be looking at. And the question is, what can you see in a hyperspectral imager? We don't know. And the Norwegian Defense Agency, with millions of dollars spent, is eager to find out. So we'll find out. It's a big deal finding the excreta of whales. It really is a big deal. I'm wrapping up, but and I've mentioned this to some of you, is the hardware looks good, sexy and all that, it works, it's robust, but it's the software. And the way in which the lab has pulled together diverse elements, all open source, to do command control, visualization, planning, analysis. You can build, I'm not sure they use MATLAB, but there's equivalent. You can spit out graphs with a button. This was exactly what we were trying to do with the ODSS. They were there about 3 years before us. And you can see with side scan and multi-beam data, it's pretty much instantaneous. And the reason it's so good now is because they were supported by the Portuguese Navy, and the Navy operators basically sat on their heads and got the whole user interface thing worked out over and over again. They hated them, but now we all really appreciate what they did. So it's very, very simple, open source. You can download it and get it to work. So where are we going? This is what I'm interested in now, coordinated observations. Phenomena in the ocean are diverse. They move. We don't know where to find them. So finding, tracking, and moving in space and time, right? With multiple robots, with multiple dimensions, aerial, surface, and underwater. What you're seeing is an image of a Berkeley UAV looking at a front, two bodies of water. This is with a standard simple GoPro camera, nothing fancy. And you can see there's a coloration difference, right? So the question is, how can we coordinate various elements to understand what's actually happening at the front? Because people don't. You can get lucky with a ship and sit there and sample. But luck at $20,000 a day on a ship is pretty expensive luck. So coordinating and using the widgets and tools that I've been working on for a long time, using temporal planning, how do we coordinate multiple vehicles? And the coordination is not a trivial coordination because it's a synchronous communication with the vehicles come and go. As when you throw a vehicle in the water, it disappears. There's no observability. You might be lucky with comms if you can set up the comm system and if you can afford it. Because as you're expending energy with the vehicle with comms, you're essentially squeezing the space of how long you can stay in the water. Comms are very expensive in the water. This was an experiment, and it says where we are going. Well, we've already gone here and come back. The idea here was working with biologists to tag what are called sunfish or mola mola. And this was last May. And to track them in space and time with aerial, surface, and underwater. So all the elements that you're seeing, we have all of them. We actually demonstrated they work separately. We were not able to demonstrate exactly this scenario because our ship that was supposed to take us out didn't really work. So we borrowed a Navy ship very quickly and made sure that the different parts actually worked independently of each other. So this is sort of ongoing work. We do have data from this experiment from last May. And where we think we should be going is essentially where a lot of people in robotics in general are going, is looking at the space from control theory to decision theoretic planning to more on information-based, information theoretic planning, where it's the data along with the notion of what you want to do. Looking at this at the sampling strategy, looking at what the data is informing you, using that as a basis for actually being out in the field. And this is where models matter, and where models matter and where the models are pretty poor, you do some form of learning. So the old sense plan act here is augmented by the sense plan learn and act, and I think the learning part is going to play a huge role. And this is general across the board, I believe, in robotics, not just in marine robotics. But in marine robotics, given how poor the state of knowledge is of the ocean, modeling is going to play a huge role. And modeling, there are ocean models, but they're very poor. But how do you improve those models if you can be in situ in the water, recover and transmit the data near real time as the model is cranking? And if the model can actually make improvements between what its predictions are and what's actually in the ocean, I think it's a huge win. We started along in that direction. And pretty much the next step is, if you look at this perspective, aerial, surface, and underwater, that's good, but it's not good enough because the scale of the ocean is very large. So where I'm hoping to go next is to start building small sats, university-built, students-led, student-designed, and launch multiple of these small sats with the right set of sensors. The kinds of sensors I'm interested in are mostly optical-based or radar-based. Synthetic aperture is a really important one. Hyperspectral imagers are really important. So imagine if you had an Android cell phone-based or maybe a tablet-based spacecraft out in space looking down, which had the right form factor and the energy level, looking at the same part of the ocean at the same time as you are in situ, aerial, surface, and underwater. You can cover a large space in very short time, and you can make predictions very rapidly of how things are changing and then be responsive to it. Things are moving constantly, and that's really the big catch about the ocean. And of course, there's a whole infrastructure that comes beyond it, but that infrastructure also leads us to what kinds of academic leads there are in doing research. And those are the three that I think are critical, and the last being pretty much the superset of everything else, which is sampling. And some of the work, as you're seeing here, has already been published. The mixed initiative stuff was with John. We've published in ICRA or IROS or something, IROS. And the whole notion is using priors, what kind of predictions can we make? The priors come from remote sensing, but the priors can come from a range of different things. And this is where a student of mine, JD, not this work, but there's another work here, right here, species distribution. Given past data on where microorganisms have been found in the ocean, what kind of predictions can you make on when you want to sample? You have 10 samplers, for example. What informed decisions can you make about where you want to sample next? So that's a Gaussian process, a standard Kriging set of techniques that he pioneered. He's now at Penn, and that was very good work, and it's some of it is still under review. But there are whole issues about sensors and so forth, which have to do with what's missing. Optical sensors, especially laser-based, the amount of energy that they consume is very high. And this is not something that all of us can develop, but I think these are motivations for bringing in people from physics, chemistry, and so forth. And laser-based optical sensors are actually crucial. looking at particle size, looking at organism size. Can you look at a chunk of the water, a drop of water, and figure out how many, what type, and what's the density of organisms? That's really, really important. And as I mentioned, I'm really interested in synthetic aperture now, given the obvious use for maritime surveillance, domain awareness, taking very rapid pictures, showing variations in the water, in the ocean, on the surface. That's really important. So, so that's where things are, and this is pretty much the last slide. And to a large extent, the work that I've been pursuing has a lot to do with how do you get machines in the water, but how do you make those decisions in ways that scale? Not just scaling in terms of the cost of a vehicle, but it's the cost of building systems and maintaining them. We don't want to keep building systems over and over again. You want to build on, once you've built the bricks, you want to keep building the house on top. And to a large extent, I believe what we have is the basis for doing lots of things, which is why T-Rex, the system that I discussed earlier, is somewhat open. Different people can participate, and we want different people to use it. And of course, it's open source. And how you build those widgets inside the reactors is again open. And it doesn't have everything solved. In fact, failure and diagnosis, failure recovery is an open issue on that. And I'm hoping we can work together on doing something interesting. So ocean science is changing rapidly. You would have heard a lot about climate change, and especially climate change with an impact on the ocean. So I think if there's even 1% of you who actually go out, start looking at marine robotics and making an impact, I think it will be significant. Simply because it's a very large ocean, lots of low-hanging fruit. Yes, it's challenging to get out into the ocean, and yes, funding is a little tight, but impact factor is extremely high. Whatever you do, the impact is extremely high. So that's it. Lots of references. Jim Bellingham and I very early on wrote a cover article, which I'm suspecting one of you reviewed and gave me some nasty comments, but that will remain unsaid. And it has sort of lays out the picture of what we think at that time, 2007 or 8, working with robots in hostile environments, what it entailed. And there's a bunch of other papers which are out there. So, thank you. So if there are any questions, comments, queries? Yeah.
So, as these vehicles become, they're valuable resources. They'll continue to get more valuable. What kind of model do you see, or how they'll be used by the scientific community, or how do they use it today? Is it, like if you look at something like space telescopes, for example, there's an organization that manages that resource. There's funding that comes, I guess, through NASA, but there doesn't seem to be an organization that does this kind of work. So how does the scientific community get access?
That's part of the problem here. To go to space, there's a monopoly, and that monopoly is called NASA. You want to go...
But it's also funding, it's also
that too,
resource.
That too. So it is that bottleneck. So if you talk to the the astronomy community, they have this very well-oiled, greased mechanism of how to get from idea conception to execution. And that involves getting a bunch of people together periodically, urging their friends, relatives, and whoever in the National Academy to write a report, which gets seen by the space committee, including the vice president, who tells the president, oh, look, there's this new idea of going to Mars, Jupiter, Pluto, whatever it is. It's very well oiled. It's there.
Applied physicists know to do that too, right?
Yes, yeah, right.
Yeah.
What kind of,
High energy physics is the same thing.
yeah, exactly.
Of course, here, so there's really, to get to space, it's NASA or ESA. To get to the water, there's NASA, there's DARPA, there's ONR, there's NSF, and their working left hand, right hand is not really coordinated. So if you keep that model, it means that these vehicles, they won't really be a national resource unless they're doing something very special, which is what Dana Yorger is doing. It's very, very special. And there is a deep submergence lab, and there's a national facility, or national to the extent that it's advertised. It's really Dana. So that's how it works. But AUVs will be, and I hope, will be like a Pioneer robot running here and running out in the ocean. And that's really what it needs to be, so that more people get access and more people actually buy into it. In the US, there is more buy-in. In Europe, there's still a lot of skepticism about using vehicles. And I am hoping that this downturn, this fiscal downturn, makes it more attractive for them to use physical robots.
Well, I'm sure you're aware of work that Paul Sherry and others have been doing here. I mean, this idea of building these really cheap devices that can go out and do something productive.
There's a singularity about cheapness. The cheapness is good, but if it falls off, if it's not robust enough to withstand the elements.
Right, no question.
So there's a whole, we're talking about ocean going here, but there's a whole cottage industry which deals with ponds, lakes and stuff, very different. They don't even talk to each other. And so the technology base for stuff that you do inland versus out in the ocean, completely separate.
Yeah.
And so I think he's targeted something which is really good and nice, and where you can actually entrain students. It's easier to go to the river here, throw things in, experiment. That's really nice. I think I just fell into the wrong pot. If I'd fallen into that pot, it would have been a lot easier.
Well, I don't know. I mean, maybe the economy will get there at some point. I mean, you were talking about these relatively inexpensive drones and things like that. Maybe the same would be true for underwater vehicles, so that you could treat them more like things you could
it is
lose some percentage of them.
So there's a qualitative difference between ponds and covered lakes and so forth. One is how long you want to be there, how rough it is and how deep it is. And the fact that the predictability of where you are in a more static environment is easier. You don't have currents in static lakes. You have currents in the ocean. And then essentially you think, when you surface, you think you're here, but you actually end up there. And at Mbari, to give you an idea, and this may be shocking to you as knowing a little bit about robotics, is the margin of error was 500 meters, right? So in a sense, we could never predict within that 500 meter range where we were, but we didn't care. Because upper water exploration is not about accuracy, it's about bulk phenomena. And the bulk phenomena we are talking about are in 50 square kilometers. So if 50 square kilometers you are here or 500 meters away, it doesn't matter. So there's a very qualitative...
When you're trying to track a front, for instance, being off by 500 meters.
You could be, and yes, that's a problem.
That's okay?
No, it's not okay. It's not okay, but the thing is, then what you do is you have to resort to popping up to the surface a lot more to get a GPS fix. So that's how you mitigate.
Or worry more about relative versus absolute. I mean, if you're tracking something and you can see when you're out of it and go like you were talking.
And the sensors really have to tell you where you want to be. You don't care whether you're, which side of 500 meters you are. You care about being in the front.
Right.
And as long as you traverse the front, you're kosher. So if I know I was in warm waters and then I'm suddenly in cold waters, I'm doing fine. If I stay in the cold water part for the next 2 hours, I know I'm screwing up. And then that means you got to wake up, go to the surface, figure out. By that time, you've actually lost the front because clearly you're not in the front. So that's how it works. It's more sensor driven.
In terms of the economics, have you ever tried selling the crafts for, say, surveying the ocean, surveying the floors, coastal waters, in order to make a better economic case for them?
So you have to tell me who's going to buy it.
Well, I know I've done projects for coastal survey, and so where you have some kind of, and so that was the kind of, I'm just wondering if there's more other types of customers, I guess more generally, and so that you could sort of piggyback on the platform on that and then equip it with different sensors depending on what task you're doing?
Not that I know of. I mean, really, the thing is, part of the problem is our psychology. We've treated both the air and the ocean as sewers, right? So we tend to disregard. It really is economic importance of the oceans. They keep saying it, but it doesn't factor into how we think and how we do things. It just doesn't. It's one thing to see dirty streets, but it's another thing to see really filthy and plastic-filled oceans because you don't see it. And there is a lot of it. So it a lot to do with our psychology.
There was that new report that just came out.
Yes.
That just came out. I just read about it today.
2-3 days, right?
2 or 3 days ago about the devastation. So that's it'd be interesting if that has any impact.
So I think where you find potential economic benefit is the industries that are working towards polluting it. You know,
Yeah.
like so oil and gas, right?
Plastics.
Yeah.
Plastics, yeah.
No, I mean people who would pay to have an autonomous vehicle explore the water.
Right. Well,
So-
the reason I said the surveying is that shipping companies
Yeah.
care about hitting the bottom, hitting things that are sticking up out of the floor.
Yeah, but if
Right,
a
but
ship
they
is,
don't-
if a ship is going to be hitting the bottom, you don't need to send anything underwater to map it, right?
Mapping is very expensive on coastal waters. It's very, very. They have these ships that come out and they trail these things behind them,
Right.
and there's a lot of inaccuracy because the higher up you are, the way the sonar.
The beams.
Yeah, they hit very differently. That's like $100,000 a day for them to be out there.
I mean,
Yeah, it's a very, very.
But again, I
expensive.
mean,